just forget about the airplane for a moment. If you have a car and driving on the sphere, on the Earth, this is really possible velocity vector, okay? X and Y. If I do this mathematics, I get another vector, right? Well, what's this vector? How does it look like? It always points in the z direction. And the amount of velocity is dictated by the value of x of your point. But as a direction, it always points in the z. So at this point, it's vertically up. It's always vertically up. What do you think? Is it tangent to the sphere?
No.
No. So it doesn't represent a possible velocity vector. Okay? Let's do the other way around, which is partial x, partial little x's times dy. This week we already did it. We will need to do it again. So 0, 1, 0, negative 1, 0, 0, and zeros times y, which is 0, z, negative y. What's the result? The result is
0, 0.
z, 0, 0, right? So this is maybe, I'll say V1. Here is V1. So V1, like we said, it's not always tangent to the sphere. Actually, most of the points, it's not tangent to the sphere. It's maybe tangent simply at this point only. Okay, or maybe a couple points. Okay? This is your V1. Call this V2. What's V2? That we get it points in the x direction only. Right? So again, here is V2 in the x direction only. As you can see, it's not tangent to the sphere. Maybe it's tangent here, for example, at this point or at that point. Okay? But magically, when you subtract and do this Lie bracket kind of thing, so the Lie bracket between x and y is these two things subtracted. V1 minus V2. This guy is minus z0x. This guy indeed is a tangent vector to the sphere, is a vector field. This guy looks like the following. Always tangent to the sphere. Okay? Always tangent to the sphere. This is a very important result. Like I said, give me any surface. I don't care about the surface. Any surface embedded in whatever space you like. This is much more generic than you can even think of. Any surface. A surface that you can visualize, a surface that you cannot visualize, a surface that is indeed a surface that is not a surface, is a space of matrices, but we can identify it as a manifold. Well, okay, if you start with two vector fields tangent to your surface and do this very weird operation, the result will always be tangent to your surface. Okay? So geometrically, it's an interesting result. If you have two tangent vectors or vector fields, I want to generate a third. Here is a means of doing it. Let's see how this can apply to mechanics a little bit. Just an example. Again, it's an example in pure differential geometry, but it's related to mechanics. Any question before leaving this example? Any question? Any question, please? Okay. Our usual example. Rigid body rotation. Yes, Joseph.
So if at a point on the vector field it produces a zero vector, does that still consider tangent to any direction then?
Yeah, yeah. Yeah, because it lies in your tangent space. Your tangent space is a vector space, so it has to contain the zero vector in it. Okay, so rigid body rotation. Anybody remembers what is the manifold? You can call it M in differential geometry, or in our own language we call it a configuration manifold. In either case, what is your manifold
Rotation
over
matrix.
which your system is evolving? The rigid body rotation.
Rotation matrix. SO3.
It's the space of orthogonal matrices, three-dimensional. This is, if you don't remember, this is any matrix in R 3 by 3. So this is a 3 by 3 matrix such that A transpose times A is identity, and we choose the option of the determinant is positive 1. Okay? Last time, the last thing that we showed in the last lecture, this was before the Thanksgiving, you enjoyed your turkey, so you forget everything, and I also forget, but I had the chance to review up before the lecture. So we showed, we proved, and it was a very simple proof, just one line, that the tangent space of this guy, tangent space has to be defined at a point, okay, it's at the identity matrix. Remember, the points of this guy is not a surface anymore. This guy is a space of matrices. Any point here is a matrix. So when you specify a point, you really specify it. So saying the tangent space of this guy at the point that is matrix identity was what? Anybody remembers? Was the space, we called it lidless of V, which is
skew symmetric matrix.
yeah, any matrix that is A transpose is negative A, so skew symmetric matrices. Okay? Skew symmetric matrices. That's fine. That's fine. What does it imply in our case? Well, it implies the following. That if R of t is a curve, right, curve on your manifold. What do you mean by a curve? It means that at any time t, it gives you a point here. So R of t is our rotation matrix. In differential geometry, it's just a curve. A curve passing through matrices. At any time, gives you a matrix. Okay? So this is a curve. Then R dot is what? R dot is what? Is what? I'm sorry, I didn't hear. R dot is what? If this is a curve, then its velocity is a velocity, is tangent to your stuff, right? So this guy is a curve in SO3 such that R at the 0 is just identity. So it passes through the identity at 0 time. So R dot at any time gives you the velocity at that time. In particular at 0, it gives you the velocity, the initial velocity. Okay? Or the velocity at this identity. Based on that discussion, where does this guy live? Where does this guy live? Yeah, I need to write here as a symbol one of our funky
Gamma.
Well, it's at a point. So close enough. Right? It's at a point. So it lives, where does it live?
T0 M or Q?
Yeah, it's the tangent space of your manifold, right? The tangent space of your manifold. Since R lives on SO3, so tangent space of this guy at the point in the manifold. The point in the manifold R of 0 was R. Right? Any question about this guy? From this first statement, here given, we deduce this. This is not given. Any question about this statement? From this whole description, so we have first, second, third, then we can deduce this. Any question about this here? If this guy is a velocity, well, a velocity always lives in the tangent space. At this point, we're talking about the identity, so it lives at the tangent space. But the identity is that simple, right? It's actually not that hard. That's fine. Well, we also recognize that this guy is simply a skew symmetric. So this means that R dot of 0 is a skew symmetric matrix, right? Skew So if your rigid body starts at any attitude, let's consider that this is the reference attitude, so matrix identity, okay? Your rigid body starts here, and will rotate. The initial R dot has to be a skew-symmetric matrix. Well, we already know that, by the way. Why? Because we know from our kinematics, we know this, right? R dot always at any time is negative omega tilde R. So if R is identity at initially, R is identity, R of 0 is identity, R dot of 0 will be what? Will be negative omega tilde, and omega tilde is a skew-symmetric matrix. Remember this omega tilde?
Yeah.
If your omega is your velocity vector, omega 1, 2, 3, the components of your velocity vector,
The main.
then the tilde is a skew-symmetric matrix. Skew-symmetric meaning zeros over the diagonal, and you put these guys in the following order.
Negative.
Negative omega 3, omega 2, and negative omega 1, and it's skew-symmetric. You can just swap them with the signs. So this would be omega 1, negative omega 2. Okay? So this is very consistent with what we have been doing so far. Yes, indeed, if R of 0 is identity, R dot of 0 will be a skew-symmetric matrix. That's fine, but we got it the very, very hard way using differential geometry. But when you put it in this language, we got to know more. Let's see what we get.